All right, now we're going to talk about motion diagrams. Well, the first few chapters in the book here that we're going to do with chapters 1 through 4 are all about kinetics or motion and how things move and how we determine how they move, all that kind of stuff. So the first thing we're going to do is a very simple way of representing motion. We're going to do this by just using dots. Now, for example, let's say you have a car, and you're in a car, and you're going along at a constant speed of 15 meters per second. Okay, what does that mean? And let's talk about speed and velocity. Speed is the distance something travels, total distance it travels over the total time. Okay, that would be the average speed. And then to get the instantaneous speed, you just do it at an exact instant. Instead of doing it over time, you make your time get really short. Velocity, on the other hand, is a vector, which means not only does it have speed, but it has speed and a direction. Yeah? So in this case, I put an arrow up here. That implies that that is a velocity instead of a speed, because it has a very specific direction. Speed doesn't have a direction at all. And so speed is what the cop pulls you over for when you're speeding, because he doesn't care what way you're going. If you're going too fast, you're going too fast. Where velocity says, oh, it matters which direction I go, and it's going to make a bigger difference as we go further along. But let's say this is going at a constant velocity of 15 meters per second. Well, one way we can represent this is we can say, oh, let's just have a device that marks the position of the car at exactly equal time intervals. And then marks it as a dot. So it would be here at one point, and then let's say 1 second later it's moved, and it's moved exactly 15 meters. If it's going at constant velocity, it goes, and all these circles are evenly spaced. Why? Because velocity, or speed, both these, are the distance it travels given a certain amount of time. So if the time is the same, and the velocity is constant, then the distance it travels between each of these has to be the same. The nice thing about this, when you look at a motion diagram, is if you see one with equally spaced dots, you don't even have to know this, you know that it's going at a constant velocity. All right, what if I have a motion diagram like this? So here's a car, but this is its motion diagram. What we see then is that the first second, if it's done every second, it depends on what your time interval is, it went much further than it did the seconds, and it got shorter every single time. So even though the dots are at equal time intervals, the distance between them is getting smaller. That tells us that the speed of this object is slowing down. In fact, it gets to the point here where it stopped. So this object is slowing down. If an object was speeding up, then it would go the other way. It would look like this. It would have close together and they would start to get further apart, and every time interval, the distance between them is increasing. So these representations tell you about the motion, and we call these motion diagrams, where you essentially put a dot at equal time spacings for every object. Let's do an example. Let's say I want to draw a motion diagram for if I throw a ball in the air. So here I am. I'm going to throw a ball up in the air, let it come down, it's going to bounce back up, and I'm going to catch it in my hand. So I'm going to do a motion diagram for that. So I'm going to do a motion diagram right after it leaves my hand. So I'm not going to do the part where it accelerates. I'm going to leave it right after it leaves my hand. That's where I'm going to start. So we're going to do it here. I'm going to do a bigger scale to this. So this is, let's say, where it leaves my hand. So this is the position 1. This is where it starts right here. Now what do we know about an object when you throw it up? But when you throw it up in the air, it's slowing down. Why? because gravity is working on it and pulling it down again. So gravity is accelerating it downward, and if you have your velocity going up, it's going to slow it down. Important thing to remember. This is key for the whole chapter 1 through 4. If the acceleration is a different sign than the velocity of the object slowing down. If they're the same, it's speeding up. So in this case, if I have positive going up, gravity is working in a negative direction. Those are opposite signs, so it's slowing down. So what happens is, it leaves my hand, it has a certain speed going up, or velocity in the upward direction. Then, as it goes up though, it's going to get slower and slower as gravity works on it, and it's going to get to a point where it's going to stop up there. So all the dots are going to come together. But then what happens? Then it starts to come back down. And when it's coming down, its velocity is now in a negative direction. Gravity is also negative, so they have the same sign, so it's speeding up. And it's going to speed up at the same rate it's slowed down, and it's going to keep speeding up all the way until it hits the ground. Okay. Then when it hits the ground, it's going to go back up again. We're going to assume a perfect bounce, meaning it loses no energy, which is not reality, but we're going to assume that. It bounces up, comes back with the same speed, but then it's going to start to slow down, and it's going to come, sorry, slowing down a little bit too much there. And it's going to start slowing down. Didn't do that very well, hold on. Until you catch it in your hand again. Because gravity is going to work against it as it goes back up again. And that is not right either, sorry, hold on. Alright, so it should come back up, and technically again it should be slowing down at exactly the same rate that it's speeding up. It doesn't stop until it gets up here. I don't know why I was putting it down there. It's going to come back to the same velocity as long as we're ignoring air friction, as long as we assume it was a perfect bounce on the floor. So those are motion diagrams. Make sure you can understand motion diagrams. You'll have a couple mastering physics problems from chapter 1 that allow you to do motion diagrams for specific examples.